Hello everyone, welcome back to NPTEL lecture series on cyclodecision reactions. We have been discussing about normal cyclodecision reaction, abnormal, that is inverse electron demand Diels-Alder reaction, hetero Diels-Alder reaction, and in the last two lectures we also talked about IMDA, that is intramolecular type 1 and type 2 reactions in details. Today what we will do, we will move ahead and then talk about two more subclasses of 4+2 cyclodecision reactions. One is called retro Diels-Alder reaction and the other one is called Alder Rickert reaction. And when we talked about stereochemical outcome of 4+2 cyclodecision reaction, so we knew that in the normal Diels-Alder reaction we get endo product as the major product. So this endo product is the kinetic product, as we all know. But if you heat this reaction for a longer time as well as at a higher temperature, this Diels-Alder reaction is reversible, which means that the Diels-Alder reaction undergoes reverse of 4+2 cyclodecision, which we can call it as retro Diels-Alder reaction to give back the starting material, that is diene and the dienophile. Now this diene and dienophile, when it is heated further, it can give a mixture of endo as well as exo products. Okay. So that means, see, for example, if you take this diene and then treat with this dienophile, that is cyclic acid, so initially it forms only the endo product. Okay. But if you heat it at higher temperature, then it goes back to the starting materials, that is this diene as well as this dienophile, and it undergoes further Diels-Alder reaction, and when it happens it gives a mixture of endo and exo, and since the exo product is the thermodynamically more stable product, when you heat it for longer time, exo product becomes the major product. Okay. So if you look at the potential energy diagram, so this is the starting material energy, and so this is the activation energy barrier for the endo product. Whereas if you look at the activation energy barrier for exo, it is quite high. But what happens when the Diels-Alder reaction takes place? Initially you get the endo product, and when you heat it further it comes back and it is reversible, you get the starting materials back, and in this further heating condition it undergoes Diels-Alder reaction to give a mixture of endo as well as exo product. But once the exo product is formed, you can see the activation energy barrier to come back to starting material is very high. So which means that exo product will not go back to the starting materials, that is diene and dienophile. But the endo product can come back to starting materials. So this means if you heat it for longer time, you are bound to get the exo product as the major products. So this is a simple kinetic and thermodynamic control concept. Okay. So now let us discuss few examples. If you take cyclopentadiene and then treat with maleic anhydride, at room temperature immediately you can see a nice solid, so which is nothing but the endo product. But if you take this endo product, or during the reaction condition itself, if you heat it for long time, then this endo product comes back to cyclopentadiene, maleic anhydride, and that undergoes further Diels-Alder reaction to give predominantly the thermodynamically more stable exo product. So the temperature plays a very important role in getting endo and exo product. And this is what you get at room temperature when you use cyclopentadiene as the diene and treat with maleic anhydride. But instead of cyclopentadiene, if you use furan, then what you get is directly the exo product as the major product. Even at room temperature, furan used to give the exo product. So this is because when it undergoes Rickert Diels-Alder reaction, the aromaticity of furan is the driving force. So, the Rickert Diels-Alder reaction is quite fast, so that the forward reaction when it happens, mostly it gives the exo product. So, this is how one can easily obtain either endo product or exo product by choosing the reaction conditions. So, this is again the same potential energy diagram as I have discussed earlier for the other Diels-Alder reaction between a diene and acrylic acid. Now, when we talk about the reversibility of cycloaddition reaction, sometimes based on the dienophile which you use, when it undergoes the reverse of 4+2 cycloaddition, that is Rickert Diels-Alder reaction, there is a possibility of getting a different diene and different dienophile. See, for example, now if you take butadiene as a diene and this cyclohexadiene as a dienophile, when you heat it, it undergoes a simple 4+2 cycloaddition to give this bicyclic compound. Now, if you heat it further, there is a possibility that it can undergo retro 4+2, that is reverse of 4+2 cycloaddition, to get back to your starting material. That means this cyclohexene ring undergoes retro 4+2. But there is another possibility, that is the cyclohexene ring on the left hand side. So, suppose if we call this as A ring, if the A ring undergoes Rickert Diels-Alder reaction, then you get a different diene and different dienophile. So, this is also very important, and when you do this with different types of dienophiles, then during the reaction condition you get a different dienophile, different dienes. So, that will be more interesting, particularly if the dienophile which goes out is stable and it does not react further. See, for example, if you take this diene and dimethyl acetylene dicarboxylate, so this can undergo intermolecular Diels-Alder reaction to form this 4+2 cycloadduct. Now, if you heat it further, it can undergo Rickert Diels-Alder reaction. Okay. So, one way is, suppose if this undergoes Rickert Diels-Alder reaction, one way is you get back your starting material, okay, and the dienophile also will come. The other possibility is, now instead of this diene coming out, it can also do in such a way that the right hand side will come out. If that happens, what you get is a substituted furan. The beauty of this reaction is the loss of acetonitrile. One can ask, the acetonitrile can undergo a 4+2 cycloaddition reaction with the product being formed, but acetonitrile is a solvent. So, you can force this reaction condition forward by periodically removing acetonitrile from the reaction mixture. Likewise, you take a similar substrate and then treat with benzene. So, what you will get is this intermediate. Now, again upon further heating, this can undergo a retro 4+2 cycloaddition to form isobenzophuran, and the other component, that is the 2-pi component, is benzonitrile. Here you get the acetonitrile, here you get benzonitrile. And more importantly, if you see this reaction, this reverse reaction is not really favorable, because the 2-pi component which is used is very unstable benzene. So, this forward reaction, that is the retro 4+2 cycloaddition reaction, is more favorable under this condition. And likewise, if you take these two, so this is the diene You can see this will act as a diene and this will act as dienophile. So, when this undergoes a 4+2 cycloaddition reaction, so this is what you get. Okay. So, now when you look at this intermediate, when you look at this bicyclic compound, you can clearly see there is a very good leaving group. Okay. So, earlier we have seen benzonitrile, acetonitrile, and here the good leaving group is nothing but nitrogen. So, the loss of nitrogen will give highly substituted pyridines. So, this way one can make a library of aromatic compounds by doing a sequential Diels-Alder reaction followed by retro Diels-Alder reaction. All this happens in one part. One part reaction having Diels-Alder reaction and retro Diels-Alder reaction in the same part. And again you can make lot of furan derivatives. For example, if you use the propargyl acetate as the dienophile, and this undergoes first initially the 4+2 cycloaddition reaction followed by retro Diels-Alder reaction wherein the benzonitrile comes out and you get these 3 substituted furan. Instead of propargyl acetate, you can use di-TMS acetylene, and the same way what you get is 3,4-di-trimethylsilyl furan. And instead of oxygen, if we have sulfur, you can do the same thing, and then what you get is corresponding thiophene derivative. So, this is a very simple reaction, one part reaction. At high temperature, you can easily remove the benzonitrile. So, benzonitrile is also a solvent, one can easily remove, and so that the forward reaction is more feasible. What are the leaving groups? We saw acetonitrile, we saw benzonitrile, we saw nitrogen as a better leaving group during the retro Diels-Alder reaction. One can also use carbon dioxide. Okay. See, for example, if you look at this diene, this is the diene moiety and you have carbon dioxide. So, after the Diels-Alder reaction, for the retro Diels-Alder reaction, the stable carbon dioxide can undergo extrusion during the retro Diels-Alder reaction. So, simple 4+2 cycloaddition reaction will give this bicyclo 2,2,2 intermediate. This upon further heating will undergo a retro Diels-Alder reaction where carbon dioxide is lost to give highly substituted penta substituted pyridine ring. So, this is a very nice method to make highly substituted pyridine in one step. And again, now if you look at this particular diene, this is the diene. Okay. Now, when you do the intramolecular Diels-Alder reaction, so you get this compound. Okay. When this intermediate is seen, now you know which one will undergo or which stable molecule will be expelled during the retro Diels-Alder reaction. Okay. Obviously, you have the nitrogen. So, the nitrogen can be easily removed during the retro Diels-Alder reaction. When that happens, it will give another intermediate. Okay. Again, if you look at this intermediate, you see the diene. Okay. Now, the loss of pyrrolidine should give a substituted pyridine. So, in this particular retro Diels-Alder reaction, you can see there are 2 stable molecules leaving during the retro Diels-Alder reaction. One is nitrogen, other one is the pyrrolidine. Okay. So, normally you look at only the loss of one stable molecule. In this particular case, you see 2 stable molecules leaving to get the corresponding pyridine derivative. So, you can take furan and then treat with dimethylacetylene dicarboxylate, and then if you heat it further, the retro Diels-Alder reaction, one way to get back the starting material, that is furan and dimethylacetylene dicarboxylate, but you can also see another stable molecule. When it undergoes retro Diels-Alder reaction, that will be acetylene. Okay. Or this double bond can be easily reduced selectively in the presence of tetra-substituted double bond. So, if you reduce the double bond, you get this bicyclic compound. Now, when you heat it, this can go as ethylene. Okay. So, when this goes as ethylene during the Rickert Diels-Alder reaction, you get the corresponding 3,4 disubstituted furandiamide. Likewise, you can take one alkoxy-diene and then treat with dimethylacetylene dicarboxylate. So, that also should give this particular intermediate. Now, unlike the earlier cases, you do not see a potential leaving group like ethylene or acetonitrile or nitrogen, but what it can do is it can undergo elimination of an alcohol, so that the more stable aromatic compound will be obtained in the end. Okay. So, what is important is what is the driving force for the Rickert Diels-Alder reaction. Okay. There are two driving forces to see that the Rickert Diels-Alder reaction is possible. One, a stable group leaves during the Rickert Diels-Alder reaction. Two, the more stable aromatic compound is formed. Okay. These are the two driving forces for Rickert Diels-Alder reaction to happen. Now, you look at this diene, and the dienophile is nar-Borna-diene. So, nar-Borna-diene has two double bonds. Assume that one of the double bonds is involved in the 4+2 cycloaddition reaction. So, if you heat these two in solvents like orthoxylene, then you get this pentacyclic compound. Okay. And obviously, the first step after the Diels-Alder reaction is the Rickert Diels-Alder reaction, and during the Rickert Diels-Alder reaction, the stable nitrogen should come out. So, when the stable nitrogen comes out, you get the diene like this. Now, again under the same condition, you can see this can also come out during the Rickert Diels-Alder reaction. So, if that happens, so this is very interesting compound, you can see that. Now, so this should give you cyclopentadiene. Okay. So, this should give your cyclopentadiene and the aromatic compound. So, two stable products are released during this Rickert Diels-Alder reaction. One is nitrogen, the other one is cyclopentadiene, and also the third important point is you get the stable aromatic pyridine compound. Okay. So, that is a driving force for this particular sequence of Rickert Diels-Alder reaction to take place. So, now if you look at this compound, so it is very interesting because it is a symmetrical compound and it is being treated with acetylene. So, when this undergoes first the 4+2 cycloaddition reaction, so you get this bicyclic compound. So, I will leave it for a few minutes to understand what exactly happened. Okay. So, this is the diene and this is the dienophile. So, it undergoes 4+2 cycloaddition reaction to give this intermediate. So, now does not matter whether this undergoes Rickert Diels-Alder reaction or this undergoes Rickert Diels-Alder reaction, it is same. So, what you lose is cyanoethyl formate, okay, and again you get a substituted compound which is also aromatic in nature. Okay. The driving force is the formation of aromatic compound, also the loss of more stable another molecule. Okay. So, now here is an example. So, you take diene. Okay. Diene has a stable leaving group which is carbon dioxide, but one can also see another stable leaving group nitrogen. Okay. So, if you take this diene and then treat with excess benzene, you get this diphenyl substituted anthracene. So, this is another classical example. So, where you can see the diene undergoes Diels-Alder reaction with dimethyl acetylene dicarboxylate to get this tricyclic compound. So, now again when you heat it further, so as I said, the driving force for the retro Diels-Alder reaction to happen is the formation of an aromatic ring. If you need an aromatic ring from here, the retro Diels-Alder reaction should take place in such a way that the other molecule which goes out is the cyclobutene. So, the cyclobutene and the aromatic compound, that is dimethyl phthalate, is formed as the product coming out of the sequential 4+2 followed by retro Diels-Alder reaction. So, now from retro Diels-Alder reaction we will move to another famous reaction called Alder Rickert reaction, which was discovered almost 100 years ago. So, what is this reaction? See, for example, if you take a diene like this, okay, and then do a Diels-Alder reaction with dimethyl acetylene dicarboxylate. DMAD is nothing but dimethyl acetylene dicarboxylate. So, that should give this bicyclo 2,2,2 octadiene system. Okay. Now, can you see a good leaving group in the retro Diels-Alder reaction? One, of course, your dimethyl dicarboxylate can come out, but that will give you the starting material. The other one, this portion can come out, but that is of no use. Okay, both will not give you aromatic compound. So, what is important is, as we have discussed during the retro Diels-Alder reaction, one of the driving forces is the formation of aromatic compound. So, both the formation of dimethyl acetylene dicarboxylate as well as this right hand side triple bond will not give the aromatic compound. The only fragment, if it goes out, will give aromatic compound is the top fragment. The top fragment, if it undergoes retro Diels-Alder reaction, will give aromatic compound. So, the driving force for Alder Rickert reaction to take place is the loss of ethylene as well as the formation of this highly substituted aromatic compound. So, this is called Alder Rickert reaction. This is also like a retro Diels-Alder reaction where a stable ethylene molecule comes out. So, if you take this diene, which is obtained from anisole by Birch reaction and then conjugation. Now, if you do a Diels-Alder reaction with dimethyl acetylene dicarboxylate, so you get this bicyclic intermediate, and which upon further heating undergoes elimination of ethylene to give this tri-substituted benzene ring. And one can do this intramolecular way. So, we have already discussed about intramolecular Diels-Alder reaction. So, this is intramolecular type 1 Diels-Alder reaction, where you can see the dienophile is attached to the carbon number 1. Now, if this undergoes intramolecular type 1 Diels-Alder reaction, so that should give this bicyclic intermediate. Actually, it is a tricyclic intermediate. So, this can undergo elimination of ethylene through retro Diels-Alder reaction to give this type of indane derivative. So, the loss of ethylene and then formation of this aromatic compound are the driving force for Alder Rickert reaction to take place. So, now again I will give few examples which you can do it during your free time. So, you take this diene and then do Diels-Alder reaction with this dienophile, and if you heat it after the Diels-Alder product, so what will you get? What is the stable group which will undergo elimination during this retro Diels-Alder reaction? Likewise, here also if you do the Diels-Alder reaction with dimethyl acetylene dicarboxylate and followed by retro Diels-Alder reaction, you will get an aromatic ring, but you should know what is the stable leaving group which will be eliminated during the retro Diels-Alder reaction. So, this is another classical example. So, where you can see the diene as a leaving group, that is carbon dioxide, but the dienophile, you see there are 2 double bonds. So when you look at this product, you should also think about doing 2 4+2 cycloaddition. Already we discussed one example where we did 2 cycloaddition reaction with benzene. Okay? So likewise, you also have to think there are 2 double bonds, and these 2 double bonds can act as dienophile in 2 cycloaddition reaction. Okay? So now we will move to another topic called Dehydro Diels-Alder reaction. So we discussed today retro Diels-Alder reaction followed by Alder Rickert reaction. The third one is the Dehydro Diels-Alder reaction. So what is Dehydro Diels-Alder reaction? So normally when you talk about Diels-Alder reaction, the reaction is between a diene and a dienophile. Suppose if one or both the double bonds of the diene is replaced by a triple bond, then that also can undergo Diels-Alder reaction. Those Diels-Alder reactions are called Dehydro Diels-Alder reaction. So I will give you an example where you can see you have a triple bond and a double bond. So we normally call it as E9. Okay. This E9 can undergo Diels-Alder reaction with ethylene to form this unstable cyclic alene. As you know, alene itself is unstable, but when it forms cyclic alene, it is highly unstable, and this will undergo a 1,5 hydrogen shift, or further some modification, some rearrangement will take place to give a more stable compound. So this is called Dehydro Diels-Alder reaction. Let us see with few examples. So now if you do this with acetylene instead of ethylene, then you get this intermediate which is highly unstable. Now this can undergo a 1,5 hydrogen shift to form benzene. Okay. Though it may be one of the most expensive methods to make benzene, the concept is to use Dehydro Diels-Alder reaction to make substituted aromatic compound. So for example, instead of acetylene, if you take ethylene and then you take diene, so this also can undergo a Dehydro Diels-Alder reaction followed by aromatization to give just benzene. Okay. So this is just to give you an idea about these are simple examples. When you go to complex example, then you know the value of this Dehydro Diels-Alder reaction. So now instead of ethylene, you can use acetylene as a dienophile, and if these 3 undergoes Dehydro Diels-Alder reaction, then you will get the rearranged product is benzene, which upon hydrogenation will give benzene. Okay. All these 3 reactions, you can see the substrates are different, but what you get is benzene. So that means there are 3 different ways one can carry out Dehydro Diels-Alder reaction to get the same product. Now let us look at specific examples. Okay. So you take this ester. Okay. So if you take 2 moles of this, then this can undergo Dehydro Diels-Alder reaction. It can also undergo dimerization in the process. So how it happens? So this is the E9 portion and this is the alkyne portion. Okay. When these 2 combine, then you get this Dehydro Diels-Alder product. As we have seen in the simple example where you formed benzene ring, now the 1,5 hydrogen shift will give you the substituted naphthalene derivative. Okay. And instead of ester, if you have carboxylic acid and then do the same thing, but in the presence of acetic anhydride, then what you will get is this is the product. Since you use acetic anhydride, what will happen? This 1,2 dicarboxylic acid will undergo anhydride formation to give this product as the final product. Acetic anhydride is well known to form anhydride if you have 1,2 dicarboxylic acid. Okay. So by doing subtle changes in the reaction condition, one should be able to make polysubstituted aromatic compound using Dehydro Diels-Alder reaction. So now one can also do this intramolecularly. Okay. So for example, take this symmetrical compound. Okay. So, now if you take this, you can see this is the enine portion and this is the alkyne portion. So, if these two undergo Dehydro Diels-Alder reaction, then you will get a very nice aromatic compound. And again, this is the enine and this is the triple bond, and now if you do the Dehydro Diels-Alder reaction, then there are two regioisomers possible. The one is this, the other one is this. Both are possible, and based on the steric reason, perhaps this may be the major product. Now look at this example where this is the enine moiety and this is the alkyne moiety, and if these two come together to undergo Dehydro Diels-Alder reaction, and you get a very nice carbazole derivative. So, this is a very easy way to make highly substituted carbazoles, and you do not need any reagents, just heat it. Under heating condition you get this Dehydro Diels-Alder products. Likewise, you can see here, so this is the enine portion and you have the double bond, and this upon Lewis acid treatment undergoes intramolecular Dehydro Diels-Alder reaction to give very nice tricyclic compound. And what is important is, you can see here this acetal, okay, that is intact, though you use zinc chloride. So, that is intact and nothing has happened. That brings the enine moiety to come closer to make sure this Dehydro Diels-Alder reaction takes place. Okay. One can also think about a similar example where the enine is from the 6-methoxy tetraene compound, and then do the Diels-Alder reaction, Dehydro Diels-Alder reaction with maleic anhydride, and you get a steroid like compound. Okay. So, now you can either aromatize by doing oxidation to introduce the double bond, or you can reduce this double bond to get fully saturated C ring of steroid. Okay. Not always it will give only one isomer during the Dehydro Diels-Alder reaction. So, there are examples where a mixture of two regioisomers in principle possible. So, for example, if you take this diene, okay, now you can consider this particular transient state where this is the enine and this is the alkyne. Now, if these two undergo an intramolecular Dehydro Diels-Alder reaction, what you will get is this product. However, there is another possibility that the top portion is the enine. Okay. In this case, we have seen the bottom side. There is a possibility that the top portion is the enine and the bottom one is alkyne. Now, if the Dehydro Diels-Alder reaction undergoes using this transient state, then you will get the other regioisomer. You can see here the phenyl is in the top, and here you see phenyl is the bottom. So, there is a possibility that when you have different substituents, and you also will end up in getting two different regioisomers. Okay. Now, again, if you look at this compound, so one possibility is this is enine, and if this undergoes Dehydro Diels-Alder reaction, you will get this tricyclic compound. However, if this is the enine which undergoes Dehydro Diels-Alder reaction, then you will get the other lactone where the phenyl group is in the bottom. Okay. So, what is possible is depending on the nature of your substrate. Here this is unsymmetrical. If your dialkane is unsymmetrical, then there is a possibility of getting both regioisomers, but if you start with symmetrical compound, then you will get only one product. So, today what we have discussed is, we started with retro Diels-Alder reaction, and then we extended to Alder Rickert reaction, and finally we discussed few examples of Dehydro Diels-Alder reaction. The main driving force for Dehydro Diels-Alder reaction as well as Alder Rickert reaction is the formation of aromatic compound as well as the loss of stable compound. In the case of Alder Rickert reaction, ethylene is the stable molecule which comes out, and also the formation of aromatic compound. Okay, let us stop here and then we will discuss more tomorrow about Diels-Alder reaction. Particularly, we like to discuss some examples on asymmetric Diels-Alder reaction. Okay, thank you.